So in addition to sequences of numbers, we can use recursion to define more complicated structures. And we can use induction to prove things about these more complicated structures in a similar way, but not exactly the familiar induction that we've done so far. So this is, what might be called recursively defined structures and structural induction, which we will get to in a minute. So let me write that down. Recursively defined structures. So here's an example. A full binary tree So let's just do a basic overview. A graph is made up of nodes and edges connecting two nodes. So we're going to talk about graph theory later in the course. For now, we're just going to give this one example of what is a full binary tree. But it's in the context of graph theory, so I just want to give names to these nodes and edges. And these are the things that are going to make up a binary tree. So a full binary tree is defined recursively as follows. A single node is a full binary tree. And if T1 and T2 are full binary trees, then so is this tree that we make by starting with a node and giving it two edges, one attaching to T1 and one attaching to T2. So this is the definition. And you can see, again, it falls into this sort of base case and inductive step model. But now the inductive step does not have as much to do with the integers. So normally the induction we've been doing before is normally you start with some smallest, usually positive integer, and then you go through the integers up from there. And this is slightly different, right? It's not clear that there's some integer that's incrementing through this recursion, but we are just defining it more abstractly in terms of previously defined things. But okay, let's make this concrete by going through some examples. So let's say this is the base case is just the single node. And then if we go one step further, to this node, we can give it two legs. And on each leg, we need to attach a full binary tree. We only know of one so far, so let's put it like that. Okay, so this is a full binary tree. And that's all we can make at this step. So step 2, we can make, so we start with a node, and on each leg, we put a full binary tree. So if we just put a node in each place, we already have that, we got this. So instead, let's put a node on this one, and let's put this guy on this leg. So it looks like this. And now we can do more things. We can put a single node on this side and put our little guy on the other side. Or we can put this guy on both sides. And that is all of step 2. And then step 3, things start to get, start to grow. So I'm not going to write down all of them, but for example, let's do a couple of examples. We start with a node and we want to put things on each of its two little legs. So maybe we put nothing on the first leg and this thing on the second leg. So we get a single node here, and then here we get like this. Or maybe on the first leg, we put this thing, and then on the second leg, we put this thing. So what do we get when we do that? We get this looks like this, and then this looks like this. And in this step, we have many more. And many more steps, of course. And I want to quickly define another property of these, which we won't talk much about today, but will be relevant to some practice problems, which is the height of a binary tree. Is basically the number of levels. So you can see that I've drawn them in sort of discrete levels when I do these drawings, and the height is the number of levels. But we can also define it recursively. In the following way. So we're actually going to take the number of levels, the way I'm drawing it this way, the number of levels minus 1. So the height is going to be like 1, 2, 3, like this. So how do we define this recursively? Well, when we want to do recursive things with binary trees, we need to return to the definition, which we should always be doing. Always go to the definition. And basically, it's similar to induction, except that this is our base case, and this is our inductive step. So the base case is height of the single vertex binary tree, single node, is 0. So you could also define this to be 1, but I guess I'm just following the convention in the book, which is to call it 0. And then the inductive step, what is the height of this tree that we get by attaching two trees, T1 and T2, to a new node? Well, we get one more level from adding this thing. And then what is going on down here? We're just getting whichever one is taller is going to be the contribution. So this is the max of the height of T1 and the height of T2. So you can see that, let's see. So this one is height 0. This one is height 1. These are height 2. All right, I'm using H and HT, so let me stop doing that. It's H. H is 1, H is 2, H is 3 here, and so on. So here is a nice definition of a recursive structure that is a little bit more complicated than a sequence of numbers. And we can also define properties of these structures using the recursive definition.